Welcome back to our penultimate tutorial of today's Future Climate Physical Basis Day. In this tutorial, we're going to be talking about how we can isolate the effects of internal climate variability and the uncertainty associated with this variability in our climate model projections. So you were just working with a multi-model ensemble where each model's projection was different due to their different physics, different numerics and discretization, and due to the internal climate variability, so the physical chaos of the Earth system driven by its complex and nonlinear governing equations. Now, since that last one is a physical source of uncertainty, it seems like it would be a useful thing to know how much that physical uncertainty contributes to our overall uncertainty in projected future climate. So are our uncertainties primarily driven by the physical uncertainty, or due to our choices made when building our climate models? Now, fortunately, it turns out we can explore internal climate variability specifically in isolation by creating an ensemble of models that have exactly the same physics and numerics and discretization as each other. And when we do that, we call it a single model ensemble. So we can use one specific Earth system model with exactly the same parameterizations, numerics, and discretization each time. We can run that model repeatedly, but with slight variations. And the differences in the projected climate of those models can tell us about the relative role and size of internal climate variability. Now, it turns out CMIP6 produces these types of single model ensemble, and you've actually encountered a parameter that relates to that already when loading these data sets called the member ID. And that member ID consisted of 4 letters and 4 numbers. The first number refers to the realization. So every simulation in CMIP6 of the historical and future scenarios is initialized using a spin-up simulation that can last anywhere from hundreds to 1,000 years to equilibrate the Earth system model's dynamics. And these realizations, or different realizations, can be produced by starting the Earth system model at a slightly different time. So maybe year 500 rather than 501, or 502 rather than 501. You can choose a different start year of that spin-up simulation to begin your actual Earth system model historical period. You can also initialize, which is the second number, with different conditions. So you can take an initial condition and you can add some noise to that initial condition. It could be random, it could be systematic, but you can do that in different ways and create different initializations of your model. You can also adjust the physics and the forcing, like different parameterizations or slightly different forcing data sets. Those last two are things that change the physical system. So they're things that we don't want to adjust between ensemble members if we're trying to look at internal climate variability, because we'll also see variability due to the changing physics or the changing forcing in those situations. So to investigate and isolate internal climate variability, we can take a set of CMIP6 simulations from a specific model that have different realizations and or initializations, the numbers associated with those, and create an ensemble that way. And just a side note is that the specific numbers themselves can mean different things for each CMIP6 model. So you often have to look interested into what is changing as you change a certain number for a specific model. Unfortunately, like I said, CMIP6 includes several of these single model ensembles, including the MPI models, the CESM model, both of which you've worked with today, as well as the GFDL and Canadian Earth system model projections. And these large ensembles can allow us to look at the internal climate variability, and that's where you're going to look in this next tutorial at how much is the future uncertainty in projections dominated by internal variability versus human model development choices. And I'll see you back here for the final tutorial where we'll start bringing in various observational data sets to our analysis.